Record. Okay. Good afternoon, everyone, or good morning, wherever you are. I don't know the time in Mexico. It could be 1 or 2 hours behind. I don't know. All right. Today, I am going to continue with the building the knowledge to get to final elements. We're going to get to final elements probably in 2 more classes. I have an announcement for the people here. Next week, the class will be online. I will send you you probably have already the Zoom meeting, the link. So I am not going to be here next Tuesday. All right, so the class is online. No problem if I yes. Yes. You prefer online? No.
Both are same.
All right. Okay. So I'm going to continue building my path to describe final elements the way I understand it. But for that, I need to build a little bit more electromagnetic knowledge. You probably, all of you probably already have it, but that's the way it goes for me. Okay, I am going to start with Gauss theorem. Gauss theorem is the closed integral of some flux around a closed integral of surface integral or area surface is equals to the volume integral of this divergence of that. I said I was going to avoid divergence. So I'm going to say the use of nabla, divergence of dv. So it just makes sense, right? Remember what this thing is. This is the flux created at a point. Okay, so the volume integral, the whole thing, will be the flux created in the volume. Let's say, I wouldn't call it total flux because you could be integrating on a smaller than the total flux, but the flux created in that volume is that. And obviously, this is the way we measure it. So, and this is how we measure it. So this is what Gauss law, that you can go and do a mathematical derivation. You can go crazy with this, with that, but it just makes sense. So if you have, let's say, a cube, we remember the cubes are the best friend of engineers. So if you have a cube there, and then you have another cube over here, and then you may even have another cube over there and another cube over there. So, and this cube is made small enough, you can say that it's just a little point, okay? And you can simply say, well, you go all the way to the point, so you can integrate, let's say you take this cube, and you integrate, and you get all the flux coming out from that flux, from that cube. And then you get the next one and the next one and the next one until you build some sort of volume. And now you look from the outside at all the surfaces of this volume, right? The 6 in this particular thing, you will find that indeed the flux is the same. You can go and eliminate. Let's say divergence. How do we define divergence? Divergence, if you remember, divergence of D will be the limit when the volume tends to 0 of 1 by delta volume, and the integral, the closed integral of dot dA. Now, if I integrate all this, dV, right? So I will get the thing that I have on the left. Divergence of D. Let me write it a bit better. Divergence of D, a volume integral of the divergence of B will be equals to the volume integral of the limit when the volume tends to 0, 1 by delta V, integral of D dot dA, and the whole thing is still dV. But you could simply also say, well, I am taking the volume integral and I am divided by the volume. So you can simply say this thing is dV. Therefore, this comes to be equals to the volume integral of, to the area integral, this is A, to the closed area integral of D dot dA. So you can have some sort of mathematical justification if you want, but this course, or whatever you call it, class, chat, whatever you want to call this, what we are doing, is mostly about physical things. So what I'm saying is the Gauss law, which is the volume integral of the divergence of the, let me change this. The volume integral of the divergence of d dv is equals to the closed integral of A dot dA. And that can be demonstrated mathematically if you wish, or or with little steps like this. Okay. Now let's switch a little bit to electromagnetic fields. And we're going to do Gauss law. Gauss law tells you exactly what we have done. So the surface integral of dot dA will be equals to the volume integral of rho v dv. Okay. What is this thing? This thing here is the volumetric charge distribution. So, and it's given, of course, in coulombs by meters cubed. That will be the units of that thing. So overall, what you are saying here is this is equals to the charge, right? So, and you can compute the charge in two ways. You can compute the charge inside a volume by adding all the volumes. Let's say you have a little volume over here, and you have charges and charges and charges distributed all over the place, right? So you could simply go and sum them all. You can say, oh, the total charge is the sum of this Qi from I equals 1 to whatever is n, and this would be Qi. You can go and compute the charge like that, which if you develop this thing, it will be a volume integral of rho v if it is some sort of distribution. It doesn't have to be uniform, some sort of dV. Or you can also measure the charge by the flux, electric flux that comes out. Now, there is always some fishy behavior, fishy interpretation of electric flux. Electric flux. Always have a little difficulty students understanding electric flux. Hey, if I tell you magnetic flux, you have no problem. Magnetic flux, oh, I can see it immediately. I can have North Pole or South Pole, and I will have South Pole, North Pole here, and I have my lines of flux, and I have no problem understanding magnetic flux. But electric flux is a bit more difficult to because we are, I think, are not used to, especially power engineers, we are not used to electric flux easily. But what if you have a charge here that is positive, and you have here a charge that is negative? And if you were to compute the forces or estimate the forces, you will see that the forces act on these charges along this way, right? Which is not different at all from this. So this and this are basically the same thing. Just one applies to electric field, another to magnetic field. So think about the electric flux as the lines where forces are felt. Wherever you felt, that's why I always prefer to see the arrows, not the extreme lines. So instead of doing this, I think a smarter way would be to see the arrows of force, right? So something like this. So the force is acting across these things, right? Force as a vector force. That F looks ugly. All right, so that is really the meaning of this. Now, um, Gauss law, which is given like that, can be decomposed like this, right? When you have the closed integral of dot dA equals to the volume integral of rho v dv, this is how we understand. This is a good equation to get the meaning. So meaning of Gauss law is the flux, is the charge. The electric charge, this electric flux is equal to the charge. So this is also equals to the charge. However, we cannot do in general volume integrals or surface integrals. So even if I don't have, I can only do those things, those integrals for rectangles or cubes, cylinders. So let's say cubes, cylinders, or spheres, right? Anything else, I cannot do those integrals. Or even if I have a cube, but the volumetric distribution inside here, this volumetric distribution of charge, is not something easy, I cannot do it. I cannot do this integral if I cannot describe it as an easy function of volume. So of course, what a volume integral is, it means that you have three integrals, rho v, which is a function of x, y, and z, and the x, dy, dc, and you can say x, y, z, right? So you could potentially, if you know the distribution of charges, you could probably integrate that equation. But in general, nobody wants to do integrals. Now, the beauty about the electromagnetics is that we don't have to. It's like that equation becomes basically the divergence. So the divergence of a of D will equals to rho V using Gauss theorem, right? So I can write this equation. Now, for rectangular geometries, I can say this divergence is dot this, which will be equals to partial derivatives d dx of dx plus d dy of dy plus d dz of dz. And this is the way to compute it. So this gives us the meaning, And this one is the way to compute it. Again, if you have such equation for a whatever distribution you have, it may not be easy to do. Right? It may not be easy to, not even solving this differential equation. The only good thing is that we engineers are trained to solve differential equations, and we're not trying to solve integrals, integral equations. So it becomes a bit easier. But for a generic geometry, there is no analytical solution either, but we have different methods. In particular, what we're going to use for this is finite elements, right? We're going to use finite elements to solve this thing. Finite elements can solve this. This is a finite elements cannot solve it. So we're going to go, the solution is going to be obtained point by point. I will want to have a discussion on charge distributions before I move forward. Let's start with point charge. A point charge physically does not exist, right? We just don't have a point charge. And when you're going to do some sort of analytical calculation, it's a very convenient model for something that looks small. So, if you put a charge in the middle of the room and you move far away, sufficiently far away, you will see it as a point. And the behavior of the field, macroscopic behavior of the field in the region where it is going to be similar to if it were a point. But it doesn't exist. So from the point of view of existence, this one is, okay, let me change it. This is a mathematical mathematical tool will be the right word. Line charge also doesn't exist, but it's very easy to see a transmission line like a line charge if you are seeing a transmission line from below, right out. It's so thin that from the point of view of engineering, it will be no problem. So this is a mathematical tool. This is also a mathematical tool, but they don't exist in reality. So, and when you go and see your finite elements program, it will not have such things. It will not have things that don't exist. Now, surface charge. Surface charge is, it happens in metals. This is the typical distribution of metals. So, and why is it? Because let's say that you have a, I put a square in there. So let me put a rectangle. And this rectangle is the representation of a subway cart, right? It's a subway cart. And Fayaz is at the terminal. And he's the first one who gets in here. So what he's going to do, he's going to find a seat that is facing forward, relatively close to the door so that he doesn't have to struggle with the people when he wants to come out. So he's going to pick the best place in the subway cart because he's the first one. Then Kashif comes in, but you don't know each other. If you know each other, you will sit together, but you don't know him. Where will you sit? As far as second best place, but a factor intervenes with you, which is you will be as far as possible from him. That's human nature, right? And then Rizzo comes, and he will try to find a place in the middle where the equal distance to them so that they don't feel offended. Because what happens if you come and sit next to him and you are the second person? What will happen? he will start getting nervous. Something is going on here, right? So we repel each other. So the first charge that you put here, you put the first charge here. So the first charge comes and put it there. The moment you put a second charge over here, this charge is going to repel, if it is the same value, it's going to repel that one, right? So it's going to go as far as possible. So if you have only two charges, one is going to be in this corner and the other one is going to be in this corner. The next one is probably going to be here, where the forces are balancing, and it's going to be go like this, like this, like this, and eventually, what you really have is a surface distribution. Everybody would try to go to the middle, right? And the charges naturally repel each other. So if you try to put a charge here, it will by itself move to a point of less energy, right? So a surface charge happens in metals because we have the free electrons. So all these charges, which are the free electrons, they move from one, they move right away to the surface. So that's why we said that inside of a metal, the field is zero because the charge is zero. So if you were to look at the charge, here will be the sum of the charges from I equals 1 to n. A line charge will give you is the line integral of the linear distribution of charge, line charge, dl, but this doesn't exist, right? From here to here is just mathematical tools. Starting here, we have that the charge will be the surface integral of the surface distribution of charge, the area, and the last one will be the volume integral of the volumetric distribution of charge. And this will be for metals. Whatever you have free charges. If you have free charges, which will happen in metals, it will happen in liquids that can move when they're charged. It will happen in everything that can move, and it will just be a surface distribution. Nothing is going to get in. And the volumetric distribution of charge will happen mostly in dielectrics. So you will have a solid distribution in dielectrics. So this is one of the reasons why we always say that the electric field in a metal is zero. So, and also the charge is all at the surface. So for me, it's easy just to draw a cylinder, because cylinders are the conductors that we use. Kind of cylindrical shape. It may be a composed of little strands and little things, but in the end, it's a cylinder. So the moment you have a cylinder in here, you will know that the electric field comes out from the surface radially, all over, but inside the electric field is zero. And the electric field is zero because the charge is zero. The charge inside, the charge in is equals to zero. So if there is no charge, there is no electric field. This is another reason why we can use electrostatic shielding. You just put a little metallic surface and nothing comes in there. At least not the electric field comes in there. Maybe some magnetic field can go through, but a magnetic field without an electric field tends to die quickly. Yeah. It's only when the electric field and magnetic field are there reinforcing each other when you can transmit things for a long distance. Why am I doing this? Okay, this is of course something that you already know, or but the reason why I am doing it is because very frequently, engineers accept the solution of a finite elements simulation as the truth. Okay, it's very easy. Oh, you simulated, you build your model, and then it's very easy to say, oh, the field is there, I can see it, and must be right because a computer cannot make mistakes. But the computers only do whatever you ask it to do. So if you have a metal or a surface or an interface between the metal and a non-metal thing, and you find that there is electric field inside, something you're doing wrong. Okay, so the same if you are doing an analysis and you have an insulator that has charge, and that charge is not distributed in the volume, you are also doing something wrong. So what I'm doing here while covering electromagnetics and a little bit of what it is, what I'm really trying to do is to give you tools. This is a tool. Come on. Tool to analyze or to have a figure of merit, to have some, I would call it peace of mind, or some verification that them is right or is giving you the right thing. It's like you have seen Fayas. I always try to show me this, show me that. And then based on that, I will say, oh, this model is correct or is incorrect. So, and the only thing I'm doing is just checking for sanity. So some verification, I would say here, sanity verification. So just to see a quick check. The same is the boundary conditions. So boundary conditions are very important. And for me, knowing the boundary conditions is a way to know that FEM simulations are right. I am going to start with the simple one. I'm going to start with a just a surface, which has material one. Material one has conductivity one, permeability one, and permittivity one. And material two has conductivity two, permeability two, and permittivity two. So, and I have some crazy field that goes in here, which I have E1, H1, D1, V1. And when it's a change of thing, it reflects and reflects. So now it goes a different direction. Let me change it. Let me not switch it too much, but a different angle that will have E2, H2, D2, and V2, right? So, and I want to know what happens at the interfaces. So the interfaces will always tell me, the solution is correct or the solution is not correct. So typically we will have metal air, we will have maybe materials with different permittivity, like if you have an insulation system on a transformer that has a paper and it has oil. So what happens in the transitions between one material to another, that is what is given by the boundary conditions. And boundary conditions are very important to specify when you do any final element simulation. I am going to start with an easy one. The easy one is the magnetic flux density. The magnetic flux density, we know that the magnetic flux density, the integral is always equals to 0. The reason is this is because it's the continuity of magnetic field. Different from electric field, magnetic field closes always in itself. Electric field can start at a point or can close in itself, depends on how it is created. So if it is created from a charge, it comes on a point. It suddenly appears from a point. And if it comes from a magnetic field that is changing in time, then it's closed. So it depends on how it is created, this electric field. But the magnetic field, it's always closed in itself. So, and that is one of the basic things we know, right? If I have a conductor that is carrying current, the magnetic field is going to be concentric lines around this. Okay? So, based on that continuity, I can go and say, well, let me put I am going to put it outside. I'm going to here put mu1, mu2, and I'm going to get a cube, or let me put it a rectangular shape like that, okay, which will have, this will be the area one on one side, and it will have this one over here will be area 2. And this is going to be an H that is going to tend to 0. I'm gonna try to collapse it to 0, right? All right. So I am going to analyze first the normal component. So the component that comes, let's say, in here, V1 normal, and it goes out here, V2 normal. The area that I need to integrate is this, right? So I will say the integral of area 1, B1, DDA1 minus the integral of area 2, B2 normal, B1 normal, B2 normal, DDA2 is equals to 0, right? These are of course the normal components. The normal components of the field. Now, why is it true? Because if I make H0, it's basically the same area, right? So whatever happens whatever enters into one is going to exit on the other one. Yeah, and I can make it small enough so that it has to be the same. Even if it doesn't have to be the same mathematically, engineeringly speaking, will be the same. So, and because area 1 is equals to area 2, and the field is not even dependent on the area by itself, but it could be, but at a point is not. So you can say area equals to area 1 equals to area 2. So I do the integrals like nothing. Bn1a minus b is 1n, b2n, a is equals to 0. I close or eliminate the area, and it's going to give me what I want. Voltage, not voltage, magnetic flux density normal 1 is equals to magnetic flux density normal 2. Okay. Why is this important? Because if I can look at the finite element solution, say I have a multi-layer physics. Yeah, so I have permeability 1, permeability 2, permeability 3, 3 different permeabilities. And I have a magnetic field that I put it in here. How do you put this magnetic field? I don't know. But it can be, for example, coming up from the windings or from a core. I can tell if this magnetic flux is perpendicular there, it will be perpendicular here at the same value. So if at the boundary I see that the magnetic field density is changing, I have a problem, right? Now, if we look at the tangential, I will look at the tangential later. I would do the same for D. So instead of having the magnetic flux density, I will have the electric flux density, which is going to be equals to D, right? And I do exactly the same. I do the integral from D dot dA equals to the volume integral of rho v dv, and I will make it equals to the surface integral of rho a dA. So this is the charge, and this is also the charge, okay? Following the same procedure, I will get D area, D1n times the area minus dN2 times the area is going to be equals to the surface integral times the area. That integral may vary a little bit if I have charge or if I don't have charge, but if I make it small enough, again, I'm doing fine. So, but now this equation takes me to a slightly different thing. It would take me D1n minus D2n equals to the surface integral, the surface distribution of charge. Okay, so what this is telling me, if you have a surface distribution of charge, the field is going to change depending on what the surface distribution is. All right, now let's look at this as an example, right? I have a cylinder, which is a conductor. Has some conductivity. And you are saying this is a metal. I'm saying this is a metal. If it is a metal, the surface, the charges will be distributed in the surface. So the Q inside, Q in is 0. And all the charges are at the surface. Okay, now, if you are producing electric field, the electric field will have to be perpendicular, okay? And the reason is because if you happen to have a inside inside the conductor if you don't have some charge, if you have some charge, the flux density will have to have a tangential component, but you don't have any charge inside. So the only conclusion is that the field has to be perpendicular to the metal. All right. Any questions to this point? I'm going to cover the other two.
I didn't follow. Could you please go over it? Yeah, here. Why equals 0?
Why is it equals to 0? Because the magnetic field is always continuous.
Yes.
So
you're assuming the area is very small.
I am assuming the area is very small, but it will happen to, it doesn't matter what area. This equation over here is valid for anything. So it doesn't matter. Let's say take a volume like this or a surface like that, right? So all the magnetic field that comes, let's say that you have a conductor over here. You have a conductor over here that is producing magnetic field. Come on. Producing magnetic field like this, right? Like that, like that, like that, like that. Some part of this magnetic field is going to get in there. So you could say, oh, in that surface, some magnetic field is getting there. But all the magnetic field, because it's continuous, that comes in will come out. And there is no, when you do the integral of the entire surface, it will give you 0. Because the flux needs to be continuous. So you're not going to have a surface where the flux is produced. So all the flux that comes in needs to come out. You're not convinced.
When you get to electric flux density, you said the electric field doesn't have a continuity.
It doesn't have to have, because you see, it will depend on the surface current, surface charge distribution.
So, because you can have monopoles, electric monopoles, and you cannot have magnetic monopoles.
Electric field can be created out of a charge. Magnetic field cannot be created of a magnet, because there is no North Pole and South Pole independent. They always come together.
So when you do the minus the U1 normal minus U2 normal, the area, you're saying the difference would be where the charge.
Exactly. So if you have a surface that has a charge, a metal, in that metal, you will have a discontinuity. So say that it's not a perfect metal, but it has some surface, some charge distribution. You may have a refraction, right? So you may have a refraction depending on what is the charge at that point, right? Yeah. So all this is to help you know if the results are right. So if you have that the field is doing something like that, and you didn't put a charge in there, you have to say this is not right. Or if you go like this and you didn't put a charge in there, you say, wait a minute, it has to be continuous. The normal component has to be continuous, and the tangential component needs to have some change in the angle, some change in the value, right?
So when there is a change, you're saying there has to be charge. But in that case, you're assuming the surface on the other side of this area is different.
At the surface, you would not know who is responsible of producing or giving that charge. You only know that at the surface there is a discontinuity.
So, when you do D times A, the A refers to what?
To a little area here. So refers to an area at the interface.
Yeah.
Okay. So this is the area. It's flat like this. So it comes at the interface. Your field comes over here, this way, and it comes out that way.
So the area is different, right? On the both sides.
No, it's the same area. Because I try to make H tend to 0. It's at the boundary. I am looking only at the boundary. The boundary could be big, but the same on both sides, the same area on both sides.
So why you writing A1, A2, but they're exactly the same?
Yes,
Okay.
they are the same. I made it over here, right?
Yeah,
A1 equals to A2.
okay. So when you're setting the boundary condition, you're saying at the boundary condition, at that,
At a particular region. You can do it at a particular point, but it doesn't have to be at a point. It could be at a particular surface that you're interested in looking at.
but when you do like, when you do the mesh, you're dividing things into mesh. You're saying at the boundary condition, the mesh on different, domain, at that boundary condition, the mesh area is the same?
Correct.
Okay, it's
So
always the same.
if we go to, if we do a final elements thing, so I have that, and you are meshing, right? You are meshing, and let's put triangles. Triangle is the most versatile shape that you can have. So you have that. On the other side, the mesh will have to be similar to that, right? Maybe inverse, but the points, the nodes need to be the same. Otherwise, you're creating a problem. Yeah. So it would be possible to do different, but normally you would just say is about the same thing. It needs to be, the nodes need to be the same. So you're going to share these things by nodes. These nodes need to be the same for both sides. Otherwise, they are not connected. Okay. And I am looking at one of those triangles, right? So I am looking at this triangle over here and this triangle over there. Yeah. So they are at the same time. They are together, and here is the boundary. Yeah. It could be different materials. It could be the same material, but then it will not be changed. Sometimes when we need finer tools, we need to look into the fields, details on something, we just put a boundary that is continuity, but just to make the meshing more efficient. To make the meshing more efficient, we could just put a boundary that doesn't represent any change of materials. We need to put a boundary every time that the materials are changing. Yeah, because you need to establish properties, you need to define the physical properties, you need to things change at those points. All right.
Okay.
Now, what if we are looking at the electric field, right? Here it is the magnetic, the flux density, electric flux density. Let me push these things to the left over here to continue. So the electric field will be epsilon1 d1n minus epsilon2, or the permittivity d2n equals to rho A. Of course, if you have that there is no charge in there, you will have the dn1 is equals to d1n equals to 2n. And so you have this equation, And if you have again, the surface, not surface, no surface distribution of charge, which will be typical of a dielectric. You will have epsilon1 d1n equals to epsilon2 d2n. And this equation, it's telling you how to design the insulation of anything that has multiple material properties. So you would say, sorry, this is the magnetic, this is the electric field. Everybody's sleeping because, Fayaz, are you sleeping?
No.
So why didn't you correct me? Yeah, no, don't let me make a mistake like this. I can make a mistake for 2 hours. Yeah. So epsilon1 E1n equals to epsilon2 E2n. Now look at this thing, right? Epsilon1n is equals to epsilon2 epsilon1. Let me do it the other way around. Epsilon2n will be equals to epsilon1 or permittivity 1, permittivity 2, E1n. And in the future, when we professors don't exist and we have only virtual professors, somebody in the class comes with the mouse and clicks in there. Crack, right? And then a virtual professor comes out, a virtual professor with lots of gray hair, glasses, a little bit chubby, with a white coat. That means authority, absolute authority, right? And it comes and explains this equation. And it says what, Rizzo? What is this equation say? Say that you are the one, because you are young, you are the one who programs the whole thing, right? And comes and click of the mouse on that equation, and then somebody comes out here, as I told you, with a white coat, with a bow tie, completely bald, and maybe some crazy hair, gray hair like this, and glasses with a stick. Okay, the small, not a big stick. And what would you say? What would you make that virtual professor say? No, but that equation is talking. Tell me what this equation is telling you something.
Oh, yeah. So when you go from one material to another material, there will be incontinuity in the change of the.
Okay, so that's correct. But it tells you a bit more. So the electric field in the end is the stress, right? This is the stress of insulation. This is stress, insulation stress. Yes, somebody wants to say anything online?
Well, Professor Francisco, well, this is interesting for me because, we use this ratio to try to control the electric field in surfaces of insulators, for example.
Yes.
We can modify the properties, we can modify the components, the normal components, and reduce maybe the tangential component of the electric field that is the most important in insulators, for example. So
exactly.
By this condition, we can modify that ratio between tangential and normal components. Yeah.
Exactly. So in the end, what this equation is telling you is that the material with the larger permeability will have less stress, right? With-
It's a transformation ratio.
It's like a transformation ratio, but so normally so the material with the larger permeability will be stressed more. Right? So, and because
Sorry.
of that, what?
Sorry, Dr. De Leon. Also, we use this ratio to show how cavities in insulation can be more stressed. No?
Yeah, very
Due to
good,
the
very good,
different
very good
permittivity.
for me. Very good. Yes. Cavities. So let's say that you have a solid piece of insulation and you have a little thing in there, right? An imperfection. So then you will know that the field is changing there because this has permeability 1 and this one will have permeability 0, right? It's an air cavity. So you will know what the stresses are. So the material with the smaller permittivity will be stressed more. Yeah, inverse. So it will be stressed more. Air is the lowest possible permittivity. So, and air will also be the one that has less dielectric strength. So if you have voids, the field is going to concentrate on those voids, and that's what you're going to have partial discharges and those things. Okay, so this is things that equations can tell you. But the way I want to use it is, let's see if final element is right. If final elements will be right. If you have a discontinuity in a change of permittivity, you should know that the field is going to change. What is what I'm saying, right? I am saying that if I have a magnetic electric field that is perpendicular here, and this is epsilon 1, this is epsilon 2. So the electric field is going to be, let me change it, put here, epsilon 2 here and epsilon 1, 2. So material 1. So this is the electric field 1. If the permeability of the other field, it will make increase this epsilon E2. So I will have a stress there. What am I doing? This is a E2, E1. So depending on the value, right? This E1 will be greater, E not equal will be greater than E2 if epsilon 1 is smaller than epsilon 2. Okay. So you can have these things. You can have a magnification of the field. Magnification of the field by having different permittivities is a big problem in most insulation system designs. Particularly the transformer is one that will give you trouble if you don't use materials that have similar permittivity. Okay, so we know that we need paper or we need several layers of insulation. Typically on a large transformer, we will have paper and oil. And we try to make these two systems as close as possible in the insulation to prevent this sort of amplification of the electric field. No silly questions.
Okay. So that means if designed properly, there can be some kind of transformer based on this. But there is a difference in the electric field.
So, which means is that you need to put thicker insulation than what you need. But it can also tell you that it doesn't matter how thick you put it, the stress is still keeps on growing, depending on the value of your permittivities. So, yeah, this is one way. All transformer manufacturers, they know that if you sometimes put more insulation, you will only create a larger stress. Yeah.
So how do you understand the stress? So
How do I understand what?
the stress. So,
The stress is electric field.
yeah, no, but how the stress behave to the stress would be maximum when there are two different materials that contact each other?
No, that will be minimum.
That would mean,
The minimum is when epsilon 1 is equals to epsilon 2. When the permittivities are the same, is when you get to the
I mean,
minimum.
when two different materials are touching each other,
Uh-huh.
you're saying that's the stress coming from, right? With two different,
You can create a stress zone by the change of insulation.
Yeah.
But sometimes you need to change the insulation. Can't keep everything together. For example, I have to go to the transformer because it's what I know best. So in a transformer, you have paper insulation impregnated in oil paper insulation, or oil impregnated paper insulation touching the conductors. But paper is not a very good conductor of heat. And the transformer is going to get hot. So you need to remove that heat. So what you need is oil. So oil will move and take the heat from wherever it's being generated, either it's being naturally or forced ventilate convection, and is going to exchange this heat from wherever it is being created to the outside. All right. But that forces you to have at least two different insulating materials. So now you're going to create stress because you have two different insulating materials.
no, my question would be, how the stress distribute in the materials?
Oh, well, according to the laws of, according to Maxwell equations, right? So let me open a page. I understand what you want to say. So say for now that I have a capacitor, right? And I have different materials. Let me just put them like this. Different materials with different thicknesses. This will make easy my life because it is so. Over here, this is epsilon 1. Over here is epsilon 2. This other material is epsilon 2. All right. So, and there is only normal field because here you have, if you want to say, here you have the positive charges, and here you have the negative electrode. So the electric field is going to be only in this direction, EX, right? But at the boundary, it will be E1, epsilon 1, E1 equals to epsilon 2, E2, right? So you will have E1 here and E2 here. And if you want to say, well, that is at the boundary. All right, so this equation needs to be equal. Therefore, if you have a higher electric permittivity, this field will be smaller. And because this one is smaller, this will be higher. So you will have a concentration of the field. You will have a concentration of the field on E2. So you may want to make it bigger as I made it here, right? The field is larger, so you have to distribute it to have to make it at the boundary will be larger. You need more material for this. So this is the equation that allows you to design for that.
So for, you need more materials, meaning, the thickness, right?
Yeah, thicker material, as you can see here. Permittivity.
It's the materials, it's all the material.
The permittivity, what it does, what it is telling you is how it forms these dipoles, right? Plus, minus, is the dipoles.
But the permittivity is the property of the material.
Yeah, to form dipoles.
It doesn't relate to the thickness.
It doesn't relate to the thickness, no.
You compensate the property with the thickness
Yeah, but I
to
mean,
soften the field.
what, in. if you-
At that point, the field is larger, right?
Yeah,
So if you have a larger field, you need more material to prevent this to break.
yes, but how, there are equations for that.
Oh, there are, of course, equations for that. I mean, you need to go, and I haven't gone this way, but you need to know what is the dielectric strength. The dielectric strength of the material. Which will be given in electric field units, right? The electric strength is the electric field. Yeah. So that it can withstand. So yes.
If we see, I have a question about the voltage. So let's say, at the, metal board at the, positive side is a voltage is V0, and at the interface between the two materials is V1, and, the right hand side is, let's say, 0. And if you, and the voltage equals to, electric field times the distance. So if you have a larger E2, does that means you are having a higher voltage on that?
Well, higher voltage difference, yes. Fallas. Let's build this thing. Can you build it? Can you do a 2D capacitor?
I'll try.
I mind putting you on the spot. If you prefer, we do it for next class. We do it for next class.
Next one will be good.
Okay.
Yeah.
All right. So what we're gonna do next class, we're gonna create a model. You need to create a 2D is fine, right? 2D infinite over there. So you just need to put this thing, right? This is an electrode. This is another electrode, just like that. You put positive, negative. You give a voltage between them. Just voltage, right? One you can put a 0 and the other equals to 1 volt. Yeah. And then we're going to measure what is the voltage here, and we're going to change the properties of the materials and see the arrows of electric field. Okay? Very good.
I'll do it if I will try now, maybe we will spend some time, so it's better for the next class.
But it would be, right now would be the perfect time to illustrate it. If you think you can build it quickly,
Yeah, I'm trying it.
okay. So let's change it to
No, but you carry on.
no. We want to are you projecting your screen? Are you gonna project your screen on the Zoom?
Professor, I would prefer it to do it first, then I will show you.
Okay.
Else I'm not sure.
All right.
No, it doesn't
Okay.
work on it.
So
Sometimes it goes.
but you are robbing people the opportunity
No,
to
no.
learn how to do it.
I have an issue with the
Yeah.
computer memory, so sometimes it's not working in my computer.
Okay, fine. Fine.
So that is
All
the
right.
reason.
Let me do the other components, right? The other components. For example, while Fallas is preparing, but you're gonna miss the class, and I don't want that.
Okay, I will do that.
Yeah.
Okay, I will share
We'll
that.
do it for next time.
Okay.
Okay. We'll do it for next time.
Okay.
Okay. All right. So tangential components. Tangential components. let's start with Ampere's law, right? The integral of J dot dA. And I am going to d dt, just always, for most of what I'm going to do, I'm going to neglect this thing. So I'm going to make it 0 because I am a low frequency person. Whoever in here is a high frequency person, are you high frequency? Yeah. So I am a low frequency. I limit myself to eddy currents, those things. I don't go to waves and those things. And for the people in Mexico, I think this is for electrical engineers, not for communications. So we can simply no displacement current. And if you are interested in the waves, well, we are not too far from the waves either. Okay, so also in the analytical thing is J is given of the units are amperes per meter. But there is such a thing as K, which will be the linear, this is the current density. Okay, and there is the linear distribution of current. It also exists. We can use it because we can see a transmission line, a conductor of a transmission line with respect to the distances, but we will use this called a line current. We can use this line current for analytical calculations, but for final elements, it just doesn't exist. And the process is going to be the same. You're going to get the meter square, and this one is amperes per meter. Yeah. So if we use this K, we can use the equation will become dl equals to the line integral of K dot dl. Therefore, it will give you that H is equals to H tangential 1. Well, I need to do a plot. I need to do a little figure. So here I have some K, some current K. So I have a boundary, and at the boundary there is some current K. Some line current K. How would I how can I see such a current? Such a current, you can only see it if you have a high frequency eddy current, so that when you have a conductor and carrying current over here at the high frequency, the current becomes a line current around the surface of that current, of that conductor. That's the only case. Other than that, it's just a mathematical crazy thing that I would actually say, let's not even assume that this is true. And just say, for the tangential components, now we have our cube. Now the cube is like this. This will be the cube, right? For this cube, the H will be just the tangential component. So we get this component and we get this component. And when it all comes and say, you're going to say H1 tangential equals to H2 tangential, or if we want to include the K, equals to the K. But I don't want to include the K. The K, I never seen a physical K ever, because not even at a very high frequency, there will always be some volume, right?
Explain again what is a shape.
K is a line current with no volume. It's the equivalent of a point charge that has no volume.
Like the current is going through.
The current is going through a filament that is so thin that you represent it as a line. That's what the K is.
And for example, that conductor case there, with different diameter, it will be different. There will be the different case there.
Well, K doesn't really exist ever. It's just a mathematical thing. K doesn't really exist in a physical meaning, because even if it is only one atom, it has some space, right? Even the electron has some dimensions. So the K is one of those, I would say, mathematical abstractions that allow you to do the calculations of certain things. Are you going to run into a K ever? I don't think so. I have been working on electromagnetics for, let's say, close to 40 years. I have never seen a K, other than for some analytical solution of electromagnetic fields. But now we don't want to get analytical solutions of electromagnetic fields. We want to get the final element solution for several reasons. Because we can only solve the reality, well, not only, but the better accepted way to solve reality is through final elements. We also tend to use final elements as a little bit too much. So, and I only trust final elements if there has been an experiment or something that validates the simulation, because many things can happen. Many things can go wrong when you are setting up a model. Many things. So you can actually validate it slowly, but building more and more on a complicated model, or use some analytical solution, approximate to see if things make sense. So in that sense, analytical solutions have some value. If you cannot do an experiment in what you have, build first, as we have done with Fayaz, build first the analytical solution, right? Build the analytical solution with your final elements. You say the analytical solution of a cylinder is this one because you know it. So you build that one first, and now you can deform the materials to the right thing. But once you have already validated that your solution makes sense. Yes.
Another question. So when you have this line current, which is imaginary, how is your magnetic, the direction of your magnetic field?
Perpendicular, right?
Yeah, how is it parallel to?
No, it's perpendicular, right? So if you have line current over here,
It's always.
the magnetic field is perpendicular.
Yeah, but why yours feels like parallel? It shouldn't be that way, right?
Oh, no, but I am going to, no, yes, I am going to go here, right? I'm going to reduce that to here.
You still need to go this way, not this way.
It goes this way, right? This way and this way. That's the component I want.
And for line current, it's going to go into the paper, not to parallel to the line.
You are right. Yes, you are right. The line current needs to be represented by this. You are right. Yes, like that. Yeah. But I am not going to use it. I am just going to say that H1 tangential is equals to H2 tangential. Continuous is continuous, right? And if I were to use V, the magnetic flux density is 1B tangential by mu1 equals to by 2 B2 tangentials equals to mu2. Okay, so I will write this equation, V2 equals to mu2 by mu1 by B1 tangential. And this one, if I were to ask Rizzo to tell me what this equation tells me, this is different from the one from the electric field, right? In the electric field, it was opposite, right? This one, what is this telling me? That the magnetic flux density is much larger or larger on the material with larger permeability than in the material or smaller permeability. When we have interfaces, iron air, say that you have interface iron air, you will have V2T equal to mu0 mu R2 equals to mu0 B1T. So you eliminate that and you get that V2 tangential is equals to mu R2 B1T. Okay, which means, let's say that you have a transformer core. I'll put it this way. So if you have a magnetic field that is in here, it means that it is magnified so much more in here, right? So it's to the point that if you do it the other way around and you have to try to say how much is B1T, B1T will be B2T over mu R2, which means that if you follow these equations, this is the core, and you have the magnetic flux here, all the flux entering here will be perpendicular, because the tangential field will be very small. Yeah, because this is a large number. Doesn't matter how much this is. Say is 10,000. It doesn't. Mu to maybe 10 to the 4. It doesn't get to that. Let's say 10 to the 4, just for the sake of discussion. So no tangential field will appear. This will probably, H tangential 1 will tend to 0. You don't get it, Rizzo. Imagine there is some tangential inside the core. Inside the core, let me put it like this. And let me put a window like that, make it like this. So you have the flux going this way. Yeah. So, but the flux hits the material always in perpendicular way, because let's say that you have a little tangential component for the discussion. This little tangential component will be magnified by 10,000 times inside the core. Yeah. So if the normal component needs to be the same and the tangential component is 10 times bigger inside, it means that the field needs to get into the core tangential, perpendicular. because the tangential component is very small. Has to be very small.
But I mean, it should be through an air gap to, because when we are
Not to an
having a
air gap,
very,
everywhere. Just like electric field is perpendicular to metal, magnetic field is perpendicular to high permeability materials.
yes.
The field enters
There's a
and
field, like,
exits perpendicularly.
to the core,
Yes.
coil, and it also, but it doesn't change the direction when it enters the iron. Because it's a.
But I'm talking about the tangential material. So,
Yeah, but the tangential material.
so I have here the surface. I have a little component here. I will have a large component there.
Oh.
Okay. So, and the other component remains the same, right? The other component here will remain the same. So,
Oh.
this is another thing. Every time that you're doing a simulation that has magnetic material and non-magnetic material, the field entering the magnetic material is always at 90 degrees. If you see the field that is not at 90 degrees, you can immediately say, this is fishy, it's not good. Something, you set up something incorrectly. Most probably your boundary conditions. You know, there are too many little details in the setting up of cases in finite elements that it's very easy to make a mistake. So when you make a mistake, to catch the situations when you make a mistake, you need to be you need to know these things. Yeah. So I can tell you this. If I see a boundary which is magnetic material, non-magnetic material, and the field is not perpendicular, I would say this is wrong. If I see a boundary, electric conductor, non-conductor, and the field is not perpendicular, I say something wrong. If I see field inside of a conductor, I say this is wrong. My electric field. Yeah.
But it has to be like looks like a perpendicular. It should not be 100% perpendicular, because.
So what is the engineering error that you accept?
Okay.
So if it is 10,000 to 1, if I offer to pay you $10,000 for some job, and I pay you 9,999, will you complain? No, right? So no. So if the permeability, different permeability is not that big. It's probably 3,000-4,000 at most. But I made it 10,000 just to have a round good number. But even if it is only 1,000, so 1%, 1 in 1,000 doesn't make any difference on what I'm saying. It's almost tangential. Almost tangential to the point that you couldn't tell with your eyes if that is not tangential. Yeah. Now, please, don't use too much, don't rely too much on the streamlines. The streamlines in COMSOL, I think they have made them better, but they used to be very bad. So use arrows plots. If you're using ANSYS does very good job with the streamlines. And probably now COMSOL does it right. I don't know. But I prefer to use the arrows proportional to the magnitude, and lots of little arrows so that you can see almost the streamlines. Yeah. All right. What else am I doing? Well, I'm just gonna write all the other equations. We will have to have also something for d tangential 2 will be epsilon 2 over epsilon 1 dt1. This is not a much too useful equation, but and the thing is that the permittivities are in general similar one to the other. Yeah. Okay. Any questions? I'm gonna change topic right now.
Like when there are corners in a geometry, so
Mhm.
like it is generally saying that charges are more in the corners than the rest
Yes.
of the surface.
Uh-huh.
So like how we can like in this general study we are just saying that charges are uniformly distributed.
Well, that's the thing. That's why we don't do analytics. That's why we don't do any analytical solution and we do final element. Okay.
So like
So-
it's like in the
You're right. For example, if you have a corner, in a material that has a corner somewhere, so you have the charges, let's say, at the surface. Let's say it's a metal, right? It is known that you were going to have a concentration of the electric field here,
yeah.
right? How can you solve this analytically? I have no idea. But if you do it with final elements, you will get it right. The same if you have a needle, right? If you have your thing is a needle like this, right? Okay. And you also have the concentration of field will be like that, much more than the field coming here, right? Even though when you know that the charges should be distributed in one way, this will happen. So final elements, we do it. Now you have two more examples to do. Okay. Yeah. So
So the like my question is that someone asked me a question like how this lightning arrestor works. So it was like the pointing, the thing which we have
Mhm.
drawn is like I was
you say an arrestor
Yeah.
or a lightning
Or it-
rod?
lightning rod.
Lightning rod, not an arrestor.
Yeah, so sorry. So the area at the tip is very small. So like the reason for that is that like the potential, if we put the
Well,
equation of a
the
voltage,
thing
potential
is,
there.
you have a house, right? You have a house like this, and you want to protect the house. So you're going to have something coming out there here, say here, and this will be go all the way to ground and it will be grounded. So what you're doing, first of all, is elevating the ground. And what you want is the current of generated by a lightning striking there to drain to ground. You don't want the current to go through the body of the house, right? So that's why you put that and you put it grounded. So you have put zero potential or ground potential at the top. So that will attract it.
Yeah, so the point is that why it is pointy? That was the question.
Oh, it's pointed because that will attract it more, right?
But
Yeah.
the reason it was like smaller the area, smaller the charges will be there. But in normal we say that when there is a corner, there are more charges.
I am gonna go I am gonna go to the subway analogy, right? Everything needs to be distributed equally in the surface, right? But in the corner, there is less surface, right? Because say you go like this, as you can see, these charges in this corner will have less space to spread around, right? Just look at the corner, right? You come here, here, here. When I get to here, I have space, but I cannot put another person right here. Right? So there will be stresses. They have to fight, and then they have to fight, and it will come out there, right? So think of the corner as the subway corner.
But here we have two corners, like the point is just like same as a corner. Here the charges are, they say that charges, but I think I have mixed this thing that in the corner the charges are concentrating more. So can we say this in this pointy second?
The same
the
thing
charges,
happens. The same
happens.
thing happens. The same thing happens. So you put a potential there.
It virtually increases the length of the rod. Virtually. The size are
I'm thinking
increasing the
about-
volume, but the point is increasing the length.
You can say so, yes.
Yeah, that's why the rod can be pointing, because to go higher, it's better to have just virtual
Mhm.
point. And with the point you have
Yeah.
increased dimension.
Look at today is extremely cold outside, right? Go out without a glove. And how are you going to be colder? With your hands, with your fingers exposed, or if you have them like this, right? So if you make a fist, you will be warmer. Yeah. So, and if you open them, you have more area exposed. So, yeah. Yeah. So for the people in Mexico, you just learned that here is extremely cold. It hasn't even reached 0 degrees in a week. So
Yeah.
we are all here freezing. Yeah. All right. Okay. Now I go to the line integrals with the purpose of having some understanding in path dependence and path independence. Of course, I am only doing this with the bad intention to define the chord. All what I'm going to do here is I am pointing to the chord. That's what I'm trying to do. In Spanish, this is el rotacional. Okay. So I am now trying to go into the chord. And let's think like a line integral that you want to move from point A to point B. And you follow two different paths. You follow the red path like that. Let's say you follow a black path like this. And let's say that you follow the orange path that goes like that, goes back and goes like this. So, under which circumstances you spend more energy going through any non-straight line than through the straight line? Of course, we all think if we go through the straight line, so if we go this way, that will be the path of least energy spent. But under which circumstances you spend more energy going from point A to point B, under which circumstances you spend the same amount of money from going from point A to point B. When
it's not evenly distributed.
You're almost right. You're almost right. So, whenever the field is potential coming from a, let's say, electrostatic field, the electrostatic field, it would not matter which way you go. So if you remember how these things are, so this is the charge. Your equipotentials are like this because your field is all like that, like that, like that. So the only work that you do is when you move in this direction and that direction. You don't do any work when you move this way. So work here is equals to 0. Work here will be equals to a negative number, and work here will be equals to positive number. So if you move a charge against the other charge when the force is being outside, then at that point you are spending money. So This type of field is called a conservative field. And in electricity and magnetism only happens when you have charges. When you have charges, that is a conservative field. Any other field, even the electric field produced by magnetic variations of with time, or the magnetic field is not a conservative field. So it doesn't matter which way you compute the work. If the field is created, if the force field is like that, is when you have a let's say the sum of the forces at each point and the distance that you move is equals to the total force, right? The energy that you expend. Now, what if this circumstance happens? Imagine now this is a river. I have a river here. And I have some whirlpools in this river. And I have, at this point, there is a whirlpool that is rotating like that, like that. And over here, there is another whirlpool that is rotating like this in the same river. And I need to go again from point A to point B. Why do I want to go from point A to point B? I don't know. Maybe there is a beautiful woman over there for a man or a beautiful man for a woman. Maybe the woman will wait for a moment, but who knows? These days, women can pursue men. But maybe there is a pot of money there. I don't know. But you have a motivation to go from A to B, right? You have a motivation. You're willing to put some money. Now, what if you are a smart and you realize that you could be taking the boat or swimming across this and then over here change to here and get to there? Hey, not only you get to your destination, but you got to your destination rested, no problem, right? And you didn't really spend any energy. In fact, you gain money on the way because you were transporting some bananas and you sold them on the other side. Right. Now, what if you go the other way around? Now you go this way, which is what we normally humans do, right? Humans, we always go against whatever is good for us. Yeah. So now we go against the current and we get there very tired. We spent a lot of energy and now we cannot do anything on the other side because we're very tired and we're finished, right, for the day. So this is a typical case of a non-conservative, field. A non-conservative field has, I don't know how you want to call it, ripples. You want to call them eddies. You want to call it ripples, eddies, whatever. So in a non-conservative field like this one, you will be able to recover energy or lose energy depending on your path. So it's path dependent. The conservative field is path independent, and the non-conservative field is path dependent. And it all has to do what the, and it all has to do with the existence or non-existence of eddies. So what makes a field non-conservative implies that you have some eddies. say, some rotation. That the field there is, it has a rotation. So, okay. If you have the same field, the same river, with no eddies, so everything goes like this. Let me actually do another. Well, let me. It's okay. This is good. Just let me put it a bit above this. So we have two different rivers, maybe the same river, but at a different time. So you want to go from point A to point B, and all the field is like that. It will be conservative. Whatever work you do, or whatever the work the field does to you, going from point A to point B, because you've traveled for free, you pay. Here you have negative money, and over here you will pay with your money. And the round trip, the closed integral of the field dot dl, round trip ticket, is 0. Okay. So, but what if the field now is like that, right? And you want to go from, again, you're still trying to go from point A to point B. Now, it will depend on which way you go, which path you follow. So now the closed integral to the round trip of E dot or F dot dl, the force dl, is different from 0. So there will be some exchange of money when you come back and forth. All systems in the world, except the electrostatic fields, are non-conservative. Yeah, it doesn't matter. Maybe a savings account in a bank, if you have more than the minimum, so that they don't charge you commission, that would be a conservative if the system. But most human systems are non-conservative, and always the customer is on the loose end, on the losing side of the transaction. Yeah, you always have to pay something. But for example, you cannot take an airplane back and forth and say, hey, that's free. I started here, they took you to one place, they return you to the same place. That's a very non-conservative way to travel. All human travel is non-conservative. But the bank, sometimes a good bank will be a conservative thing. You put certain amount of money, may not create any money, and they will keep your money there for as long as you want and give it to you back entirely. And they actually gave you a service for that, but not money, but they gave you a service. If you have a savings account that gives you interest, so you are traveling with the eddies, and if you have a savings account that charges you service, you're traveling against the eddies. And banks will try to push you to the against the eddies. Yeah, they would trick you into those things. All right. So just to finish, I have a second challenge. Design a mathematical tool based on what we know to find whirlpools at points. So, what way would you go? Why line integral?
It is over the
So
surface.
you will go line integral of whatever force of field of force, DL, line integral.
over
I
the
will put it,
surface,
I put it round over
the surface.
Why over the surface? Because you've seen the equation. Yeah.
Now I know that you want to prove the curl.
Now because I want to prove the curl, yes. So explain the equation.
It's just like
Limit when the delta area tends to 0. And what you're saying is because we have seen before the 1 by delta volume, right? Integral of the field dot dA, right? So you say, okay, this was giving me the amount of flux. So now you say, okay, I'm gonna take the same and make it different. But this is just the closed path that we said, right? We're just let me delete this page. So you're just going around. You're gonna go this way or the other way. So round trip. So you're gonna take the round trip there to know if you spent money, you made money or nothing, you're gonna go round trip. All right. So that's why we go round trip. And this is exactly the money integral. This is the money integral, is not the quantity integral. So did I spend any money going in the round trip? And in the round trip, I describe some area. For example, here, if I go from, let's say that the red, I'm going to change the direction of the red. Change the direction of the red and go the other way, right? It goes here and here and goes back and goes back and goes back. And this is a closed path. So in the end, I made money, I paid money, or I got exactly what I wanted. This is what this work integral tells me. Okay. And this is what we call the curl. Is this. So you follow a path, right? You follow a path, and the area will be this area, right? Yeah. If you see, the more area you have, the more possibility of having curls you have, right? Now, because we want to determine on a particular point, we're going to get rid of the area, we're going to collapse it to the point, and and design the tool. And I think this is very important. It's important that I don't want to cover it now because I need you to be awake. Yeah. So I think I will open it now for questions, comments, and things like this. Let me stop sharing. So I will open it for comments or questions and whatever you guys want to do. First of all, let me ask the Mexicans. It is okay with the way we transfer the files, or you don't need it because I don't know if you need it. Fermin.
Well, it's I can see it. I mean, I can download, and it's good to have it, I think.
So I will continue. I don't know exactly if I learn how to do it, but I have Carlos here. I will try to post the notes the way they using that system. It's better than sending email and clogging your inboxes, right?
Yeah, yeah.
So
I think it's okay, like you are doing that.
Now, if you are already taking the moving, you don't need it. It's all right. I will still post it because it's very easy.
Okay.
I think it's very easy. I will just keep on posting it, and I put them in YouTube. So, but you have the links there to the YouTube recordings, and maybe some crazy person that is not involved with this will watch it. And I don't think I'm gonna become a millionaire with a YouTube based on a final element. The market is too small. Yeah. Okay, so any questions, any doubts? We're going to complete the core next session. It's better if we if I keep it for the next one, because I'm not going to complete it today, and I need fresh minds. Did you make any progress with the simulation?
I'm not sure they're right or wrong, but it's there.
Okay, so let's do this. You need to share your screen. Are you connected to the
Yes.
to the Zoom? So we have the simulation of the capacitor. I am going to
I'm not sure it's right or
so it's right or wrong, but I think it's going to be right from what I saw. So share your screen, please, Fayaz.
okay.
So what we're doing is
in the geometry, I created two rectangles, and then the material, one is mica and other is glass. And then that's the aero surface for electric field.
yeah, but I need to change the permittivities.
Permittivities, okay?
Yeah.
So we can go with add material from blank material.
No, can we just change it there or no?
Let me check. Mica.
Because your permittivities, I think, are very similar.
Mhm.
So it was 6.
Yeah.
And what is the value of the other one?
Glass is also 6.
Oh,
Yeah,
that's why
that's
why
right.
we don't
Almost
see
the same.
anything.
Yeah.
All right. So put 1 and 6.
Okay. So 1.
1 and the other, leave it the way it is.
Okay.
So now run it. So it's a parallel plates capacitor. The voltage is applied on the left side. And first of all, get rid of these colors.
Okay.
No colors.
No, sir.
They are very good to impress your wife. Okay. But they are useless for engineering. Now, make these arrows smaller. There you go. Oh, not that small. No, what you need is fewer arrows. 2 minutes. You come in.
Pure arrows. How much? 10?
Then there you go. So I think it was too small. Can you change the permittivity to 2? The one you reduced to 1, this one, put 2 instead, right there for yes. Value
31.
right here.
Yeah.
Put 2, because 1 was too small. The magnification was too large. The problem is that you put mica with 6, it's too high. The other one is too high, but this is good. So now we can see that the field on the which one is which one, Fayaz?
Okay, let me see. This one is mica,
Mica is 2.
and this one is glass.
Okay, so
Glass is 4.2 almost.
so the field stresses on the material with the smallest permittivity, right?
Mhm.
That's what is happening. Show me the arrows.
So mica is 2. So now the arrows.
Okay. So which one is mica? The one on the right or the one on the left?
I forgot. Okay, let me see. Mica
It
is
has
this
to
one.
be the one on the right.
Yeah,
So
yeah.
the one on the right has a
Mica.
what is the permittivity there?
It was 2.
2. So the field it becomes
Yeah.
stresses more the insulation on the right. So if you want a uniform stress, you will have to make larger this material, right?
So if we like go into the electric field norm.
Don't
then-
don't give me the norm. No,
Okay.
no. Give me the equipotentials. If you have the equipotentials, give me the equipotentials.
This is no.
Well, those are, but the
It will
colors
go and disable.
and disable the, there you go, yes. So now we can see the, how the potential distributes. So, it has to go from 1 to 0, or from 100 to 0. Yeah. So, so this is what we do. Yeah.
The probability on the right hand side that material is small enough. Can that make the voltage at the interface higher than the left?
Yeah, but it's already not the same, right? So I don't know what line is this, but this is not 50 volts, right? There are 100 volts applied from one side to the other.
Like 66 should be.
And here is
I mean,
one,
is it,
it should be 1/3, right?
2/3.
Okay, 2/3.
I mean, is that possible that voltage in the middle make it can be higher than the left side?
No,
But
no,
Unless you change the materials.
no, but.
no. When you say that the voltage in the middle here be higher than here,
Yeah,
no,
But if you,
Yeah, sorry.
if you just do the mathematical calculations.
it's not possible.
Okay,
You cannot have voltage interpretation as
yeah,
transformer.
I know.
Unless you have a negative permeability. Permittivity.
Until it's not.
No, and there is no negative permittivity. It can be 0, so it can be the same, but it cannot be. And 0 only happens to superconductors. Oh, no, not even. No, what am I saying? It happens to conductors. All conductors will just give you the electric field straight. If you put a conductor on any one of those, the field will just go directly to the other side. Okay,
Okay, so the next was.
what was the next?
Where was that? I think next was to see, I can put it now. Was to see the electric field, the electric field density at the corners.
Oh, okay. Is you build the skies too?
But I forgot where I. Now is in the sketch.
Oh, you're gonna start?
It's just 2 minutes. 1 minute.
In Mexico, they may be hungry. What's the time in Mexico now? It's 2?
2 p.m. Yeah.
Yeah.
2 o'clock.
So they are hungry.
The air and the copper.
And put the charge.
You know,
1 volt.
sorry, this one is like delete. And remove. And 1 volt.
1 volt.
Okay, so mesh. All that. Okay, but if we go to this thing,
Yeah,
this
This
text,
is the
density,
electric field intensity.
so
So you can see right away.
the corners it is more.
Yeah.
Can you show the direction of the field?
Yeah, we need the
Arrows.
arrows, surface arrow. See, some arrows are like more in magnitude.
So
So
that means if you have not enough charges in metal, then the field doesn't have to be perpendicular to the surface.
The field will be perpendicular to the surface no matter what.
But if you see there,
Zoom into this corner. Zoom into the corner. Okay.
maybe too much.
No,
Too much like this.
No, put more arrows, smaller arrows.
more smaller arrows. More than that?
More.
Maybe just.
There you go.
So,
Just smaller, make them smaller.
okay, yeah, so
Okay.
on the left side, those arrows are not perpendicular. to
Yes,
the-
well, because
Yeah,
they want to be perpendicular. Go to the subway example.
yeah, I know,
So
but.
you want it to be like this, with your arms, you want it to be with your arms all right, but now you have to go like this.
Yeah, but this is also because those arrows are not in the boundary.
Yeah, you need more arrows.
No, I think you have to choose like where does the arrow origin.
No, but they will not be perpendicular. The other lines that you have there, those are the lines of the force, these ones.
Yeah.
Those are the
Yes,
lines.
those are.
So
But-
indeed, they are perpendicular here,
as
but
long-
not in this corner, not in the corner, because
No.
you have the overcrowding effect. So the charges want to be uniformly distributed, but here there is not the same amount of area for the given volume, right? So they concentrate in there, and that's why they give you this crazy thing.
No, that's not proportional.
So first, can you me a little bit to the,
So
first, can you me a little bit to the corner? Yeah,
So these,
okay.
So here is almost perpendicular, here is almost perpendicular. In the middle, they try to squeeze because it has to be the same. They cannot, it doesn't fit any longer. Yeah, the charges accumulate too much in there. Yeah. All right. Well, this thing, you cannot solve it analytically. It's not, there's no analytical solution for such a thing. Yeah. All right. See you, everybody. You stop everything. Stop sharing.
So, like, should I share,
Just stop
I'm done, yeah.
Stop sharing. That's it. That's all you need to do. All right. Okay. So see you next Tuesday. To the people in Mexico, I'm gonna be actually in Cancun next Tuesday. I will be in a warm place next week. So, but we still have the class on Tuesday at this time.
Okay. Thank you,
And for the
Professor.
people here, you are gonna be here. You can actually come here if you want.
Yeah.
I'm presented here. Yeah. All right. See you then.
See you.
Take care.
See you, thanks.
Yeah.